Welcome today for the session of evolution of the RISC-V architecture. It will be a 30 to 40-minute session, and we'll also take the questions. Please type your questions in the chat window here, and I will try to answer them as soon as I can. Since we are recording the session, please keep yourself on mute. Okay. So we have been hearing about, like, I'm sure since you're joining this session close to festival on a Saturday morning, you guys are excited about RISC-V. A lot of things happening in the RISC-V world. Like Qualcomm is bringing RISC-V based wearable platform, Wear OS by Google. Then in India, there are a lot of news about RISC-V becoming a global movement. India is planning to play a key role. The leading electronics firms are partnering to drive RISC-V ecosystem. A lot of companies, as in well-known companies, are part of the RISC-V ecosystem. So there is a lot of news and growth happening in RISC-V system, and it's better to know what that fuss is all about so that we can figure out how does it help us as in people who are actually working in semiconductor. So let's see what is all this about, right? So what we are going to talk about is one, what is a RISC-V ISA? ISA stands for Instruction Set Architecture. Then we'll talk about RISC-V base instruction set and extensions. Some comparison. We won't go into deep since this is an introductory session, but some comparison of RISC-V and MIPS, and comparison of RISC-V and ARM, and how does it compare with X architecture, and let's looking at the big picture, where does it go and what are the things and opportunities in this domain. So first of all, right, what is actually an ISA? Okay. ISA is kind of a contract between software and hardware. Okay. Previously, if you remember, right, as in I don't know how many of you remember, but let's say 2 or 3 generation, I would say 20 years back or 30 years back, or even game consoles today, right? As in, so programmers wrote directly the code which was written can only work on that particular hardware. And this happens today itself. For example, if you're familiar with, let's say, Xbox or PlayStation, as in, it's very, very possible that the game, you actually have to release different versions of the game. Let's say the companies release different versions of the game, one which will work on PlayStation and another which will work on Xbox. Okay, and this used to happen. So basically, you are writing a particular piece of software which can only work on one hardware. Okay, now, of course, that creates a lot of challenge because the software development cost increases because of that. So people came up with an idea that can we have some sort of agreement between what hardware common functionality is and software, so that basically for each and every piece of hardware, we don't have to create a separate software. Okay. And that's where ISA came up and ISA was designed. It's a contract between software and hardware. The instruction set defines what information can be passed from the compiler to the hardware. So compiler is aware of the hardware while the software is not, and it's a compiler job to convert that particular software to hardware. Pre-60s, so it's almost like 50, 60 years back, it did not exist. And as I mentioned, for some of the hardwares, it still does not exist. So previously, programmer directly used to code for machine-specific hardware. So program for one hardware did not work on the other, like we are talking about the game consoles, like separate games for Xbox or PlayStation. Okay, so that's where ISA was designed. So it's kind of a layer between hardware and your software, and there is some agreed upon things in that. Based upon that, compilers can convert a software to a particular hardware machine. Okay, so that's an ISA. It's kind of an agreement. This is also known as architecture. Okay, so ISA is sitting at the boundary of hardware and software. So there is software, which is application, compiler, your operating systems, your machines on the top of it, and this at some level equally applies. This used to be applied for computers, but this, you can say, right, as in today's cell phones, tablets are actually computers, right? So this kind of applies there as well. And the definition of ISA, what does the definition of ISA include? The definition of ISA includes what are the data types supported by hardware, whether it's a 32-bit hardware, 16-bit hardware, floating point is supported or not supported. What is a memory model? What are the registers which are present? And what is the instruction set that define the machine language? And RISC-V is one such instruction set. Okay. So why do we care about ISA, right? Right? A lot of times ISAs become tied to kind of markets. Okay, so for example, let's say x86, okay, by Intel and AMD is kind of an ISA which basically work on a lot of laptops, but is not used in more than 90% of the cell phones and tablets. Similarly, ARM instruction set, which is used in more than 90% of the cell phones, is not being used in servers. Although those things are changing, but basically ISA is one of the most important interface. It's where software meets hardware, and it's a large cost to port and tune ISA dependent code in modern software stack. So not only ISA is important, but the compilers, the ecosystem around it, which is also known as software stack, those are also very, very important. And your compiler optimization, like how good a code gonna run on your hardware, is the compiler, which is driven by your compiler optimization, is also very, very dependent upon ISA, right? So what are some of the available ISA instruction set architectures? One is x86. You might have heard about it. We'll also talk about it a little bit more. Then there are ARM, V7 and V9. These are something which is known as proprietary ISA. So basically, what is the meaning of proprietary? That if you have to use these ISAs, you have to pay some royalty, some charges. You can't just use it for free. Yes, if you're using ARM ISA, there are multiple kind of contracts which exist. Similarly to x86 as well, but you can't just use it for free. If you want to use it, you cannot make products using these just for free. You have to pay, as in these are proprietary commercial ISAs. Okay. Now let's compare that to what is happening in RISC-V. Okay. So RISC-V, and then of course, right, as in if you have, of course, like these proprietary ISAs are advanced, used in a lot of devices and computers, and so there is a lot of ecosystem and infrastructure around it, but they come at some cost. And sometimes, let's say you are a startup or you're an early stage company, you may not have that much money, right? So RISC-V was designed trying to solve some of these challenges to be commercially viable. It's not just for hobbyists and it's so that you can create commercial products, but an open source architecture. What is the meaning of open source? Is anyone can use the ISA for free, as in you don't have to pay for the ISA, but it is strong enough to make commercial products robust and efficient and flexible. So how is it different from other architectures? It's open source. It uses a base set of instructions, so it can be used across a wide kind of devices, microcontrollers, computers, servers, cell phones. So it can support a wide range of embedded systems, from simple embedded systems to high performance data servers as well. And it also offers both defined and customizable extensions. So you can have, let's say, floating point extensions over the base instruction set architecture. So it kind of tries to create an open source version of an ISA which anyone can use, with the power of able to use it on simpler embedded system to more complex like data servers or even AI hardwares as well. So it supports both existing and future design. So one of the things which happens with ISAs, as you start using it for longer duration of time, they become really, really complex. So it's kind of designed in a way so that even future designs can be handled by support of extensions. And this is what has been growing, right? RISC-V community actually has more than 500, and this was the number a couple of years back. This number has grown. Industrial and academic members who are there, including Western Digital, Nvidia, Microchip, Samsung. I was showing about previously, Qualcomm now. So there are a lot of players, a lot of ecosystem which is developing around it. But if I have to say, it's still not there as in terms of software ecosystem which exists for, let's say, ARM or x86. But it's growing. So it's something we should be aware of. There are a lot of, plus it also drives innovation. So there are a lot of innovative companies which are also coming up in India also. So that's how it's been evolving. Okay. So let's talk about little bit detail. Again, I'm not going into full detail because there is a wide audience, but I'll talk about, if you want to learn more, how you can learn more. So RISC-V has various base instruction sets and extension. And the reason it's designed that way is so that it can support a broad range of processors, starting from small, inexpensive embedded processors to high performance multi-core and even multi-threaded processors as well. It has 32-bit, 64-bit, and 128-bit instruction set. Typically, how it is denoted is you will see something like RV. Then what is a bit of that, and then some letter. E stands for embedded version, which usually is 16 registers for very low cost processor, but you do have RV64i, RV128i. Okay, so they support 32-bit, 64-bit, and 128-bit instruction set. Most common extensions which are there are floating point related extensions. Then there is something called compressed instructions and atomic instructions. Now, one of the important thing, all RISC-V processors must support one of the base architecture, which is base architecture means basic support of basic instruction set like 32, 64, or 128i. The advantage with that is, even in worst case, like what happens with a more complex instruction set is you can kind of do more complex instructions. So all RISC-V processor must support base instructions, and using extensions instead of changing the architecture or ISA allows both forward and backward compatibility between microarchitectures. So there is a question on what is an atomic instructions. So I will talk about it. That is a little bit offline because I want to not lose the flow of this and keep cover all the points I want to cover in sessions today. So what's different about RISC-V? It's simple. It can actually be extremely tiny compared to other contemporary ISAs, and that's because of legacy reason. So basically, people took a clean set and started with the mind frame of what are the challenges which earlier ISAs had run into, and created a clean slate implementation of a new ISA. It's extremely modular for extensibility, customization, like what we just talked about, floating point. It's stable, it's community driven. So there is a RISC-V community, which you can also join. You can contribute to it once you reach a certain level. So it's community driven, open source, and basically brings in the advantages what all open source things do. Now, so RISC-V actually has many similarities to MIPS architectures, okay? But it also eliminates some unnecessary complexity. The similarity includes is similar assembly and machine code formats, instruction mnemonics, register naming, stack and calling convention. But there are some differences in terms of branch and jumping being program counter relative, strict definition of source and destination register instruction field. So again, I'm just telling you, basically there is, so MIPS came earlier. Okay, RISC-V is similar to MIPS, MIPS at some level. Actually, the company MIPS now is diving into RISC-V, taking RISC-V to new heights. So MIPS used to be an earlier architecture. Some of you might have studied in the college. So it's basically similar at some level to MIPS, but it is very different from other architectures. ARM, let's say comparing it to ARM, ARM is also a RISC architecture, and ARM processor dominate the mobile devices arena. Both ARM and RISC-V use smaller number of machine code formats. But how ARM differs is it includes conditional execution, complex indexing mode, push and pop, and as in, don't mind if you're not able to understand some of these terminology, we can talk about it later. We do also have a computer architecture course which talks about some of the terminologies. And again, if you want to learn something in depth, I'll be talking about there are a few more things which we have and which we are launching. So maybe if you want to get into more details, we have options for you. So some of the ARM feature actually are now our CISC features. So ARM is not truly RISC anymore, but it's important to reduce. As in, so basically, ARM is actually not, kind of used to be, I would say, purely RISC, but it's not anymore. It's similar to becoming x86. So it's not purely RISC anymore, reduce instruction set anymore, and which has been done to reduce and program and memory which is needed for embedded or complex handheld devices. But that then leads to more complex hardware. I actually have a YouTube video which talks about RISC versus CISC and why it helps to be sometimes be CISC architecture to reduce hardware. So you can search on our YouTube channel on VLSI Deep Dive. So it has a lot of similarities with MIPS, with ARM as an ARM architecture not being pure RISC anymore. So there are a lot of differences between RISC-V and ARM. Now, comparing it to x86 architecture. So most of the PCs and servers architecture that is used is x86 architecture, and it's one of the oldest surviving architecture. It was originally developed by Intel. AMD also sells x86 compatible microprocessor. So it dates back to 1978. So you can imagine almost like 50 years, right? Intel and AMD have created a lot of instruction set and capabilities, right? So basically to improve, to survive these 50 years, all the technology advancements which have happened, the architecture actually has become very complex, and a lot of things came in which were not even imagined. So that's why it's kind of became clunky and cumbersome. But one important part of this is it has a very good software infrastructure, software compatibilities. The people have done a lot of optimization in terms of writing compilers. So that is where it's basically has been very, very successful, and there's still a lot of ecosystem which exists for that. x86 actually is a complex instruction set, or computer instruction set. Now, because it has survived for a lot of years, a lot of features have been added. As you can imagine, it's not very straightforward. It's kind of a little bit messy because it contains a legacy, almost 50 years of decade of changes. So your instruction may vary from 1 to 15 bytes. Opcode may vary, maybe 1 byte, 2 byte, 3 bytes. So it's very complex compared to simplicity of the RISC-V instruction set. So that's one of the challenge. But the advantage it provides, it's widely used. It has survived the test of time, and it is a good ecosystem. By ecosystem, I mean if you write a code and you have, let's say, x86 computer server as in software is able to really optimize that code and put it on any kind of x86 hardware you have. So one question which comes up is what is RISC versus CISC? So I'm not going into too much detail. For example, I'll just take a small example. Let's say you want to multiply two numbers, right? Now multiplication can, if we remember our school mathematics, multiplication can be it can be, let's say, a lot of addition, right? As in you can actually do multiplication by addition. and or you can just directly, let's say, design your hardware to do multiplication. And that's basically at a very high level difference between RISC and CISC. So RISC will have reduced instruction sets. So to do a particular operation, basically the operations will be simple, but you might take a lot of cycles to do it. Whereas CISC can have complex instructions, like, let's say, multiplication, for example. It's directly you can do in hardware. Let's say that is an instruction. Now, because of that, a single instruction may take more cycles, may have more complex hardware. So this is the difference which comes as RISC works on a principle of reduced instruction set and taking more assembly lines to do a particular operation, whereas CISC will kind of have complex instructions. So some of those things can be done in a single instruction. So let's say you want to do multiplication, will be a simple complex instruction known as mult. So it's closer to higher level language like C coding, and that's where CISC starts becoming complex and loses the simplicity of like RISC-V kind of RISC architecture. So RISC operate will kind of break it down into steps and try to do multiplication. Now, what are the types of RISC-V instruction types, right? So there are arithmetic and logical instructions like R type, I type, results and source instruction, U type. So again, I'm not going into detail, just flashing it so that you know as in what the kind of instruction set which exists. And we do have courses which go in details on this. There is memory access kind of instruction set and control flow kind of instruction set. There are also a lot of YouTube videos. So this is an awareness session, but a lot of YouTube videos also you can kind of go into details of these instructions. Now, let's talk about what is the big picture. Where do we go from here, right? So RISC-V is a RISC architecture, which is a reduced, simple kind of instruction set. x86 is a CISC architecture. So going back to our earlier example, there will be complex instructions which are supported. So because of that, x86 will have shorter programs because the complex instruction is equal to a series of simple RISC-V instructions. While x86 architecture again has a hodgepodge of features, it has too few registers and instructions and very difficult to decode. But x86 is firmly entrenched because its software compatibility is great, and this also kind of applies to ARM kind of architectures as well. Okay, so but RISC-V has been growing very fast. As in Wilson Research Group founded that 33% of ASICs and FPGA projects incorporated a RISC-V in at least one processor, and that's around 3 years back. So it's even going further. There are CPUs, there are workstations, peripherals, office equipment, wireless devices, across the wide spread of devices. It's growing. So if you are someone kind of in hardware design, it's important to know RISC-V, or even if you are in embedded space, you should know, be aware about RISC-V because it's coming, right? As in, the devices which are going to use RISC-V is coming. Of course, the software ecosystem will take time to develop, but it's basically growing at a very fast pace. So total market for RISC-V IP and software is expected to grow to 1 billion by 2025 and maybe even further. So basically, the point I'm trying to make is it's important to know RISC-V. It's important to, like, whether you're a hardware designer or embedded programmer, it's important to kind of get into understand what is going on this. And if you kind of have a dreams about creating your own startup, let's say hardware startup, then RISC-V is one of the important thing you should know. Okay, the applications basically it spans industries, data center, automotive, AI/ML, edge computing, IoT devices, telecom, and communication. It's all of these. It's coming up, as in there are companies which are purely based upon RISC-V. There are some of those companies actually have been funded within India as well. So there are more than 2,200 RISC-V members across 70 countries. It's growing. Since 21, the membership is already doubled. It's been used across universities, chip design, design services, software companies. So the onslaught is coming, is what I'm trying to say. Okay. Now there is a specific question. Someone asked how to start building a RISC-V processor on our own on open source tools like EDA. So what are the suggestions for that? Okay, so let me tell you. Okay, so we do have courses and content catering to various kind of engineers which will exist or which will start to exist in RISC-V ecosystem. So one is hardware designers, right? So we do have a course on RISC-V which talks about microarchitecture, design, RTL, and verification. So this goes into details of how can you design a simple, let's say RISC-V design, and then basically what we also get into detail of one of the open source low risk processor developed by Google for embedded applications. So I'm just sharing the link of that. This is when if you are a hardware RTL designer and you want to look into the microarchitecture and designing of a RISC-V processor. Then we also have a complete 4-week boot camp on RISC-V, which looks more at an architecture level. So basically not at a microarchitecture level, not at an RTL design level, but how you can build applications on RISC-V. So that's another course which exists, which you also can check on our website. Okay. There is one more thing which we exist. So if you're an embedded designer or someone who loves working on hardware, we actually do have something known as RISC-V Ninja platform. And then let me actually show a little bit more detail. This is something which we recently launched. So let me go into a little bit more detail of that. Just let me share my screen again. Okay. So we do have launched, which is basically more in the embedded space of learning, as in this is RISC-V based learning. We've launched it with the Indian Electronics and Semiconductor Association, ISA. And basically, what are the features? It provides hands-on learning, step-by-step instruction to gain mastery in designing RISC-V based products. So you're designing products using RISC-V on a RISC-V board that we provide. So we have instructors, we have in-depth training videos. You can create multiple kind of applications, robotics applications, IoT applications, automated home applications. We do have more than 20 training modules, which include smart card reader, servo motors, joystick, object tracker, flight controller system. So how do you do it? As in you just basically order a kit from us. The kit, and it's basically right now we're just giving it at a throwaway price of rupees 4,999. This kit contains a board, RISC-V based board, one of the most promising processor in India, Vega processor. It's developed by CDAC, so the kit contains that. Then it contains an RF tag reader and all the necessary components you need to kind of start working with this board, wires, breadboards, data and programming wires. And you also get a login access with this, which gives you login access for all the training videos, which we'll talk about more than 20 training videos. Then there is a RISC-V community. You get access to that, and you also get access to our specific RISC-V based job portal if you're looking to kind of explore, get into RISC-V further. There are more than 20 modules. Once you purchase this kit, you get free access, lifetime access for all these modules as well. Design flow, logic design, talking about introduction to RISC-V, introduction to microprocessor, how this particular board was developed, introduction to embedded program. So this is more suited for a person who is trying to make products using RISC-V, more on the integrating RISC-V processors with other kind of application to create a final product. So it's kind of more, okay, if you want to build a product for India, for world, it's the right set of thing for you to buy. And also basically you can actually, it opens up a lot of job opportunities for you if you're looking to do in the RISC-V space. And there are more than 20 modules. The final module which you can do actually is developing a flight control system, With that, you get live access to our RISC-V Ninja community, MetaVLSI's job portal, and dedicated support. And once you complete all mandatory modules, you actually get a RISC-V Ninja certificate with it. Something which kind of, and this certificate is basically by MetaVLSI and ISA, supported by Future Skills by ISA. So it has a lot of value in the market. As in once, but the requirement is you have to kind of complete all the mandatory modules to get this certificate.